So far, you've seen the Chernoff bound, and you saw the applications to population estimation and quicksort, and now we're going to start jumping in to actually proving a number of non-trivial results that have appeared in papers over the past few decades, and these will sort of highlight the power of randomized algorithms, and especially the power of these sorts of arguments about simply just using binomial or Bernoulli random variables. And one sort of important classic result. So I'm going to sort of club these together into what I will call importance sampling. And this technique will become clearer and clearer. And I will also, maybe this will go over the next few lectures. I'll show you some recent results that I was able to get in sort of the applied world using importance sampling. So the first result that I want to talk about is this is an old algorithm of the Karp-Luby, and also the journal paper has Karp-Luby and Madras in 89, and the Karp-Luby paper was 83. For estimating the number of solutions of a DNF, which is disjunctive normal form. So recall that a DNF, which is disjunctive normal form, which we can think of as an OR of ANDs. So we'll think of our variable x going from x1 to xn. The xi's are Boolean. And our formula, phi of x, can be written as, for example, x1 or x2 not or x3. And so x1 and x2 and not x2 and x3 and x4, or x10 and x15 or x5, not x5, so on and so forth. Each of these is called a clause, and this is a disjunction of clauses. Each clause is given by ANDs. This is called a DNF. Now, my first question is, can you solve satisfiability for a DNF? Can you solve satisfiability for a DNF?
Yeah, just exhaustively. There's better methods than exhaustively.
What is the polytime algorithm? Yeah, what is the efficient algorithm?
Oh, none exists. Well, we don't
know.
No, that's for CNFs.
Essentially.
For DNFs, it's trivial, right? Pick a clause and satisfy the clause. So in this case, you said x1 to true, x2 to false, x3 to true, and x4 to true. So satisfiability for DNFs is polytime. Indeed, it's a simple, trivial linear time algorithm, right? So there are, and I'm just going to use M clauses. So satisfiability is trivially linear time, right? You could basically just do it in O of M plus N. You pick up a clause and you can read out a solution. But what about the counting version? So the counting version is how many satisfying assignments does phi of x have? Does this make sense? So you want to count the number of satisfying assignments. So where phi is again a DNF. So satisfiability is easy, but you want to count the number of satisfying assignments. And turns out this is, and there's a fairly simple reduction that this problem is really Sharpie complete. What this means is if you can count the number of satisfying assignments, then you can actually, in a DNF, then you can actually count the number of satisfying assignments in any Boolean formula. So you can reduce counting in any Boolean formula to counting in DNFs. And the problem is Sharpie complete.
N DNF?
Sorry?
What is N? Is this an N DNF?
No, N, I said in a DNF. Yeah, something may have...
No, as in the linear time, so the order of the... So it should be order of the number of literals, right?
Order of... So, I'm sorry. So, yeah, you're right. It's an N DNF. The N is the number of variables here. N is the number of variables. M is the number of clauses. Does that make sense? So, you can just... I mean, you probably don't even need a dependence on M. You can just read it off. I'm just saying that this is what it takes to read the input. But it's actually just O of N. You don't even need the M over there. So this problem is Sharpie complete. So what this means is that determining the number of satisfying assignments, I mean, it's not just, it is clear it's NP, it's more than NP hard. It's more than NP hard. But remarkably, what Karp and Luby give is an algorithm, is a polynomial time algorithm that can approximate the number of solutions, sort of arbitrarily well. And so let me first give you the, some definitions here. So an FP-RAS is a fully polynomial randomized approximation scheme. Okay, a fully polynomial randomized approximation scheme. What this means is, so let's just say that for phi is your formula. Let's say that the number of satisfying assignments I will refer to as satisfying S of phi. So there is a polynomial time algorithm. So in this case, it would mean polynomial in N and M, or I should say, for any epsilon greater than 0, there is a polynomial time algorithm that runs in poly N, M, and 1 over epsilon, such that the output is an epsilon approximation to S of phi with high probability. So what this means is that the probability, again, this is the probability over the randomness of the algorithm, that the output is contained in 1 plus minus epsilon of the true answer is at least 2/3. Now I'm going to use this as a short form. I'll say output is in 1 plus minus epsilon, really to mean that the output is less than 1 plus epsilon times that, and at least 1 minus epsilon times that. Okay, so this is the shorthand that I'm using, and the probability is actually, or you can even just say just greater than. Okay. Now remember, I only guarantee a 2/3 probability of success, but you can use the median trick to boost to 1 minus delta with extra log 1 over delta factor in the running time. So this is what an FPRAS is. It's a fully polynomial randomized approximation scheme. It means that there is a polynomial time algorithm that runs in polynomial of n, m, and 1 divided by epsilon, such that the output of this algorithm is an technical. Okay, so it's often written as a 1 plus epsilon approximation, not epsilon approximation, I'm sorry. A 1 plus epsilon approximation to this. Now, what 1 plus epsilon approximation means is that your output is basically within 1 plus minus epsilon of the true output. Okay, so the output is within 1 plus minus epsilon of the true output, and this happens with probability at least 2/3. Now, as I said in the previous lecture, all you need is a constant that beats a half, because then you can use the median trick to boost your probability of success to any desired 1 minus delta with an extra log 1 over delta in the running time. So is the statement of the result clear? Is the statement clear? Any questions? Okay. So now let me give you the algorithm. Now what Karp-Luby or Karp-Luby and Madras give is an algorithm and this is again a randomized algorithm that runs in specifically we'll get the simple algorithm is going to be O of m square n divided by epsilon square. Remember, n is the number of variables, m is the number of clauses. So this is the basic algorithm. Then there's a more advanced clever version that actually gets m times n divided by epsilon square, and I'll discuss this once we finish this. Okay, so remember m clauses and n variables. So let me introduce some notation here. I'll say S.
Wait, question.
Yes.
I think I just lost what this line meant. The last line of the previous section. So 1 minus epsilon times the assignment of phi.
Which one? 1 minus this one.
Yes, the one below the arrow. Yes.
Yeah, so I'm just saying that what I mean by this is somewhat of a shorthand that I have invented. What the shorthand means is this.
Okay.
Right? It's just saying I'm just writing out in math what it means for an output to be a 1 plus epsilon approximation. So typically you'll see in papers and results they say we have an algorithm that is a 1 plus epsilon approximation. What that means is that the output is within 1 plus minus epsilon of the truth. Right? So this is the quantity that you want to estimate, sort of the truth. This is your output. This is the estimate, and the estimate is within 1 plus minus epsilon. Does that make sense?
Okay, and how would that look like?
What do you mean? How would that? Yeah, you mean what? So the algorithm will basically spit a number at you.
Right. So this S of phi, which is an assignment to phi.
No, S of phi is not an assignment. S of phi is the number of satisfying assignments.
The number. Okay. All right. Okay, now it makes sense. Okay, I'm sorry.
It's the number of satisfying assignments is S of phi.
All right, I missed the hash sign.
Yeah.
Thank you.
Yeah. Okay. So does that make clear? So you're counting. You're not just
Yes,
finding a
yes,
satisfying
yes,
assignment. Yeah.
yes.
You're counting. So this is again a remarkable power of randomness here, which is to count exactly is sharply hard. Right? We do not believe that there's a polynomial time algorithm. On the other hand, you can get as close. You can get within 1 plus minus epsilon with a polynomial dependence on 1 over epsilon. So this is the remarkable power that the randomization gives you. in terms of developing an algorithm. Now, of course, the question of whether this power is required, whether randomness actually gives you something more, which is the P versus BPP question, is it's a much bigger topic in complexity theory. In general, it's believed that it doesn't give you more than a polynomial speedup, but I don't want to go there. I just want you to look at this and say, here's this problem for which one can easily show it sharply hard, and yet one can devise a clever randomized algorithm that gives you such a strong guarantee. Okay, so now let's go to Karp-Luby. Now first I need to give you some notation. So S sub I is the set of satisfying assignments to the ith clause. Okay, that's a set of satisfying assignments, and we want to estimate the union of S sub I, of I going from 1 to m. We want to estimate this sum, and I am just going to refer to this sum. I will denote this as capital A. So capital A is what we want to estimate. Now let me ask you a question. Can we determine the size of S sub I for a given clause? So suppose I gave you a clause. Like for example, here is a clause x1 and x2 complement, or x and x3 and x4. And suppose I gave you this clause and I said, what is the number of satisfying assignments just for this clause? How many will that be? Right, there are n variables.
N minus how many ever variables are in that clause to the power of 2?
Almost.
Sorry, no, 2 to the power of that, sorry.
2 to the power of that, right? So it's going to be 2 to the power of n minus li, where li is the number of literals in the ith clause. Right? That's the number of literals. Here would be 4, so it would be 2 to the n minus 4. So it turns out we can determine the number of satisfying assignments for an individual clause very easily. We can just look that up. So this is easy to determine. So this is also easy to determine, which is the sum of all the SIs. This is easy to compute. So one way to think of this is you have a collection of sets. Now these sets are exponentially large, but you only have m of these sets. So you have these sets, there are m of them. You know the size of each of these sets. That's the size of S sub I. So you can get the sum of the sizes. And I'm going to denote this as B. This I'm going to call B. And this is A. And so what Karp-Luby give is essentially they give an algorithm to estimate A divided by B. Now what can you say about A divided by B? Can you tell me something about the range of A divided by B? What is the largest it can be? What is the largest that A divided by B can be? Sorry?
It's at most 1.
It's at most 1. Exactly, right? Because it's the union of sets. And clearly, this is going to be positive. So now, if I can construct a Bernoulli, whose probability of being heads is exactly A divided by B, then I can just use the Chernoff bound to get my concentration. And this trick, which is you have some quantity you want to estimate, you find something that is larger that you can compute, and then try to estimate the ratio using a Bernoulli. This is a very common and powerful method in randomized algorithms. Okay? So let me actually write out the algorithm and then I'll give you the idea. Okay, I'll write out the algorithm. So the algorithm, so KLM, the algorithm. So I'm not going to, okay, so it's going to say for, let me use j from 1 to t. So this is something that I'm going to call the number of samples, and I will set this later. I will show you how the setting of this will naturally come from the Chernoff bound. So the first thing you do is you actually let me, yes, okay. So what we're going to do is we're going to choose the ith clause with probability Si divided by the sum of Si's. So this is sort of like your important sample here. So you choose a clause with probability proportional to the number of satisfying assignments. So we've computed all of these quantities beforehand. So we can essentially set up a data structure to do this. We can, for now, let's not get into the details of how exactly you will do the data structuring, but this is something that I will come back to at some point. So you choose the ith clause with probability proportional to Si. Then you will choose a uniform at random satisfying assignment X to the ith clause, which in some sense is saying that you're choosing X uniform at random from this set Si. So you picked a set uniformly at random. Then you choose a uniform at random satisfying assignment to the clause that you just picked. Now here's the clever bit. We'll say if X does not satisfy any does not, okay, so let me write this out in a different way. I'll say if there exists some I prime less than I such that X satisfies the I prime clause, set my random variable xi to 0, else set xi to 1. Finally, what I'm going to do is I'm going to output the sum of xi, I going from 1 to t. There were t iterations of this. So I divide by that times b, and recall that b was just this sum. Okay, so let me just read through the algorithm again. So for j going from 1 to t, so that you're just going to do, I'm sorry, I should say j. This is j. And okay, so just to be clear, my indices I refer to clauses, j refer to trials. These are called trials. So there are going to be T trials. J represents the trial number. These are independent trials. So I'll say independently here. Right? So this is all independently. Right? Everything is done independent. So first you choose the ith clause with probability proportional to the number of satisfying assignments of that clause, which we just argued can be computed. Then you independently choose a uniform at random satisfying assignment to that clause. Now here's the trick. So we're going to construct a Bernoulli. Xj is going to be a Bernoulli. And all the xj's are going to be identically distributed. They're IID Bernoullis. We will look at all the clauses that are less than I. Remember, the clauses are numbered 1 to m. Look at any clause that is less than I. So you're just numbering the clauses. Look at a clause I prime. And if x satisfies any clause that is less than I prime, you just set the trial to be a failure. Otherwise, you say the trial was a success. You look at the fraction of successes and you multiply by b, and that is your output. Any questions about the algorithm?
Maybe we'll go into it a little later on, but why do we look at only the previous clauses?
I'll explain that. So that is part of the trick as to how to set this up.
So you're essentially trying to like avoid double counting by doing this?
Exactly. This is a way of sort of unbiasing the fact that if you had an assignment that satisfied many clauses, then it would appear too often. And this is a way of downweighting that, of unbiasing it.
So, sorry, the xj means x, the capital S is assignment, right?
No, capital X is a random variable. Small x is an assignment.
Okay, okay.
Capital X, from in this course, capital X, capital Y, capital Z are always going to be random variables.
Okay.
Okay, any further questions? All right, so let's continue. Okay. Now before so let me write out. So remember, I still haven't told you how to set the number of trials. Okay. Let me refer to this quantity as the random variable y. And so my main theorem is just going to be y is in 1 plus minus epsilon of a. Sorry, there should be no. Y is in 1 plus minus epsilon of a with probability at least 2/3 if we set t to be omega m divided by epsilon squared. So if you do m divided by epsilon squared trials, you will succeed with high probability. So what's the idea? Before I write out the proof. So again, let's look at this collection of sets. So a trivial estimate to the union would just be b, right? We could just say that b is some kind of trivial estimate to the union. The problem lies in the intersections. The problem lies in the intersections. Suppose we uniquely assigned or associated every x, which is a satisfying assignment, so we uniquely associate it to a single clause that x satisfied. Okay, so let me explain that further. Let me consider the set of tuples x comma I, where this means x satisfies the ith clause. How many tuples are there? How many tuples are there? How many tuples?
There's 3 of them.
Phi of them. Okay. No, I mean, phi is just the name of the
B.
B of them. Yes, B. Exactly. It's exactly B. Right? Because you can sum over all I going from 1 to n. How many clauses satisfy the ith clause? Well, that's exactly S sub I. So they're exactly B of them. Right? So this is your denominator. So if you consider this set of tuples, then you're exactly getting this. Now, suppose we assigned, associated, not assigned, associated x to the clause of minimum index that x satisfied. Sorry, poorly written on my part. I meant we associated x to the satisfied clause of minimum index. What this means is I look at all the clauses that x satisfies, but I associate it to the one of minimum index. So let's say x is associated to the ith clause. What does this mean? This means x does not satisfy the I prime clause for all I prime less than I. That's what it means to be associated. Right? How many tuples x comma I correspond to associations? So how many tuples correspond to associations? Any thoughts?
Exactly A.
It's exactly A. And why?
Because if you x appears maybe in multiple, the problem with the original estimation is that x might appear multiple times associated with a different number. So as long as every x is associated to a single number, you basically partitioned the intersection, and it's only going to belong to one of the two.
Exactly. So, I mean, sort of an alternate way of saying this is that every x in the union is assigned to just one clause. So the number of associations, so how many tuples correspond to associations, it's exactly the union. It's exactly that, which is A. So how many tuples correspond to associations? Exactly A. Okay, so does this make sense? So now let's look at the proof. Okay, now let's go to the proof. So this is the idea. The idea is that if you look at the number of associations, it's exactly A. If you look at the total number of tuples, it's B. So if you pick a tuple at random, so the idea is you pick a tuple uniformly at random, check if the tuple is an association, right? And so the probability that a uniform at random tuple is an association is precisely A divided by B. And that's exactly what the algorithm is doing. So let me first assert that. So let me write out a small claim here. I'll say that step 1b selects a uniform at random tuple. So let me show you again what step 1b is. So remember, I chose the ith clause with probability proportional to the size of Si. Then I choose a uniform at random satisfying assignment X from the ith clause. So let me think of this as producing the tuple Xi. This is the tuple that I get, Xi. I want to argue that this tuple, this is being produced uniformly at random. So what is the probability that the tuple Xi is selected? Well, first you have to select the ith clause is selected in step 1a, right? So the first thing you need is you have to select the ith clause over here. And then once you select the ith clause, then you have to select X times the probability that X is selected conditioned on the ith clause was selected. Right? And so what is the probability of the first one? What is the probability that the ith clause was selected?
It's inversely proportional to the number of clauses.
No, it's not necessarily, right? It's
Si by that sum.
by the sum. So it's Si divided by the sum, which is B. Okay. What is the probability that Xi is selected conditioned on the ith clause being selected?
So that is dependent.
It's just 1 over Si.
1 over Si.
Yeah, should be 1 by Si, right?
Exactly. So these things cancel out to give you 1 divided by B, which is now uniform distribution. And that's why you selected things proportional to Si. By the way, maybe, I sort of ran through this a little quickly. Do you see how to choose a uniform random satisfying assignment from a clause? How do you choose a uniform at random assignment from Si? Again, let's just use our running example of this being the clause. Right, so this was your clause. How do you choose a uniform random element from Si?
You could choose a random number of them to be satisfied from 1 to the length, and then for each of those things, choose one of them randomly to be satisfied. Does that make sense?
Little more precisely. So here's your clause.
So I guess I'm gonna choose a random number of the, like, I know at least one is going to be satisfied.
No. I said choose a uniform at random satisfying assignment that a random
Yeah.
for the ith clause. So let's say I gave you this clause.
Yeah.
Okay.
I think, yeah, so you choose a random number of them to satisfy the clause.
Random number of which?
Like,
of these?
between 1 and the length of the clause.
That's 4. So
Yeah.
all of these have to be true, though. It's an and. This is an and.
Oh, right. Sorry.
How to choose
I'm still thinking in the, like,
SI.
conjunctive.
Yeah, this is a DNF. So so what do you do?
You choose from all the cases where those 4 are true.
You just choose from all the cases where so you set x1 to 1, x2 to 0, x3 to 1, x4 to 1, and everything else is set with probability half to 1 or 0, uniformly at random. Right? You set all of these to true and everything else is uniform random. And that's how you choose the uniform random assignment. Does that make sense? Okay. So here's the claim. The claim is the probability that 1b selects a uniform at random triple. That's the proof over there. Okay, so that ends that claim. Now, step 1c checks if xi is an association. Right? That's exactly what this step does. It says if there exists any I prime less than I that satisfies so that x satisfies the I primed clause, it's going to set that random variable to 0, xj, which is for the trial. Otherwise, it sets it to 1. So, it checks if this is an association and sets xj to be 1. If and only, well, I should say that if and only if this is true. So, the probability that xj is equal to 1 is exactly, I'm sorry, if the number of tuples that are associations divided by b. We just argued that the number of tuples that correspond to associations is exactly a. So the probability that this is equal, that probability that xj is equal to 1 is exactly a divided by b. Okay. All right, so now we need to choose t. So let's look at that part. So remember, I said the expectation of xj is equal to a divided by b. So let x be equal to the sum of j going from 1 to t of xi. And again, by linearity of expectation, this is equal to t times a divided by b. Right? That's the expectation of x. And so by the multiplicative Chernoff bound and a union bound. So I'm not going to work this out explicitly, and I expect the scribe to do so. The probability that x is not in 1 plus minus epsilon times the expectation of x is less than equal to 2e to the minus, you can get epsilon square times the expectation of x divided by 3. Okay? Now what we need is we need a lower bound on the expectation. We need a lower bound on the expectation. So now here's my question. Give a lower bound, non-trivial lower bound, to A divided by B. What is the worst that A divided by B can be? Any thoughts? Because you need a lower bound on the expectation to get an upper bound over here. So let's just recall, this is A is the union of M sets, and the denominator is the sum of the sizes of M sets. Can you give me a lower bound on this?
Well, I guess in the worst case, all the sets are the same, and
Okay.
so the size of the largest SI.
Okay, good. And so what is the lower bound you get?
A.
What is the lower bound you get in that case?
1 over m.
1 over m. Because this is at least, I can just look at the largest size, right? I can just look at the largest size over here. I can lower bound the union by the largest size, and this is clearly at least 1 over m. So now, voila. Now the expectation of x is at least t divided by m. So the probability, this is not in 1 plus minus ln of x, e of x, minus epsilon square t divided by 3m. And now you see that if you set t to be omega of m divided by epsilon square, you can get this thing to be less than 1/3. Right? Indeed, you can put a log 1 over delta here, and you'll get a 1 over delta. You don't even need the median trick here. You can directly get that. So therefore, x, which is the sum of successes, can be used to estimate the expected number of successes, and recall that the estimate, the output, is equal to the output, just to show you again, the output that we got, this is capital X, so it's x divided by t times b, right? That's what the output is. That is x divided by t times b, and the expected value of the output is simply the expectation of x divided by t times b, and the expectation we said was t a divided by b divided by t times b is exactly a, and so therefore you plug all of this in and you'll get that the probability that the output is not in 1 plus minus epsilon of a is less than 1/3. Okay, and that then ends the proof of Karp-Luby. Okay, so what I'll do is I'll pause here. We'll stop for 5 minutes. I want you to ask me questions, and I'll clarify the algorithm. Okay, so now we're back to Karp-Luby, and now I'm going to talk about a very non-trivial improvement to Karp-Luby. Okay, so what is the running time? So remember, we argue that we can set t basically to be O of m divided by epsilon squared. Okay, what is the running time of Karp-Luby?
Well, for each of the like for each iteration so I guess t times
Yes.
You have to compare. You have to get the initial random uniformly at random example, which
Yes.
takes I guess O of n time, and
Yes.
then you have to compare it for each of the clauses before the clause that you did it, which is O of n.
Exactly. So you have this O of m cost here. Right? So good. So let's look at each iteration of the loop. This is going to cost you O of n because you have to basically write out this assignment. And then this is going to cost you potentially O of m, or at least it's O of m. It's it depends. Okay, so I don't want to get too much into how you build appropriate data structures for this. So I just want to think of m being much larger than n. So I don't want to optimize the dependence on n for now. So you could think of this as taking m times n, because you have to visit all the clauses that are less than the ith clause. So you're going to read each individual clause. Each reading of that clause is n, and there are potentially m such clauses you need to read. So what you get is a total running time. So I'll sort of keep that there. The running time is O of m divided by epsilon squared, that's the number of trials, times m times n, which is O of m square n divided by epsilon square. Does that make sense? So this m comes from the number of trials, and this m comes from checking for association. And this n, the n basically comes from the fact that you have to read each clause, and the potential length of each clause is n. Okay? So does this make sense? So you have quadratic dependence on m. And now this is an extremely... This is a very subtle improvement. We can improve this to O of mn divided by epsilon square using a subtle observation and a fairly clever... You need a fairly clever fix for this. Clever fix. Okay, so let's kind of go back, and to give you the intuition behind this, and for the question as to how do people come up with these ideas, wait till you see this idea, because this is really a gem. Let me consider two separate scenarios. These are sort of the opposite scenarios. This is that the SIs are disjoint. Okay? And in this case, let's say that the SIs are nearly identical. Okay? So what is the value of A divided by B over here? What is the value of A divided by B over here?
1.
1. What is the value of A divided by B over here?
The size of the vector is 1 by B.
1 by m.
Yeah, so the previous one. Yeah.
Yeah. So 1 by m. Right? Okay. So now let's go back. Remember that we set remember that we went here. The choice of t really was this. This is what the choice of t depends on. Right? The number of samples. We basically set t to be larger than the reciprocal of this quantity, which is a divided by b. Right? We said we need a lower bound. So what should t be here? What is the t that you need when a divided by b is 1? What is the choice of t that you actually needed to get concentration? Right, so you have a coin which essentially appears heads all the time, or nearly heads all the time. You can assume that maybe there's some slight intersection. How many coin tosses do you need to estimate the bias accurately?
1.
You need 1, exactly. So you need like 1 over epsilon square. Right, that's really what you need. And what do you need here? How many coin tosses do you need to now determine the bias, to determine this heads probability accurately?
M over epsilon squared.
M over epsilon square. So it turns out that in this case, if you're in this case, you don't really need that many trials. But if you're in this case, you definitely need those many trials. So it seems like, well, if you're in, you don't know which case you're in, obviously. But then here was a very clever observation. Okay, so let me bring back the algorithm to you. So remember, this discussion of the t, is talking about, so I want to zoom out a bit. Right? This discussion of the t is the discussion of that m, right? So if you reduce t, you can reduce that choice of m. But you also have this other m, which is checking for the association. Now let's go back to the situation and say how long to check for association here. And let's just imagine as a thought experiment that instead of actually going over the I primes in order, maybe we went over them randomly. Now observe that if you find an I prime so that x satisfies the I prime clause, you can immediately end. You don't need to look at all the clauses. Does that make sense? So how long to check this association if the SIs were disjoint?
That would take mn?
Yeah, it would basically take mn, right? Because it only satisfies one clause, and so you have to go through all the other clauses to determine that. So essentially, it's going to take something like m times n, right? So again, let me ignore the dependence of n here. But what about in this case? How long? Now this is somewhat of an ill-posed question.
It takes like O of 1.
So sort of on average, exactly, on the average, this should only take, so I'll just say that this is O of mn. I'll just say these are O's, and this should just be O of 1, because everything is assigned to a one unique clause, but it satisfies almost all clauses. So if you were to go over these randomly, then you would very quickly determine that it did not satisfy the clause, and then you could just stop. Does this make sense? In this case, the number of trials you need is small, but each association check is expensive. Here, the number of trials you need is large, but every association check is cheap. The product of these are actually both m over epsilon square. And indeed, it seems like it is the product of these which is the runtime. What we did was we bounded the worst case trials and the worst case associations and said this is O of m and this is O of m, and we get O of m square. But the remarkable observation is that when the number of trials is actually in its worst case, then the association check is cheap and vice versa. And what we will do is actually exploit this to give an mn divided by epsilon squared algorithm. Does this make sense?
So whatever we lose in one side is actually made up because of the distribution of the solution sets, and therefore that same loss is made up for in finding the association.
Exactly. But yeah, you need to set it up so that you actually, that we do this all in an unbiased manner. But you're exactly right. Whatever loss you gain because the a divided by b is decreasing, right? So as you go down here, as you sort of interpolate between this, the number of trials is going up. But it turns out the gain is that the association check is going to become faster on average. And so the cleverness is in exploiting this so that you actually get the product of these.
So basically, if you do a bunch of checks at the beginning and they're all really fast, then you want to stop testing earlier?
Good. It's a good observation. So it's kind of like that, right? It's kind of like one way of thinking of this is you could start by very few trials, and you can see, are you actually succeeding? Because if you did a few trials in this case, you would immediately get things that are associated. But if you did a few trials here, you wouldn't see anything that is associated. So now you have to do more trials until you start seeing associations. Right? So the game is all about how many associations are you going to see. And once you see the right number of associations, you can stop. You have to be a little more careful here, because in this case, even though the association check is cheap, to find an association is going to take you a long time. So we're going to have to redesign the algorithm. But I hope you see sort of the weakness in the current approach, or rather the weakness in the trivial bound. You see it here, and now we're going to try to exploit it. Okay, so
if we just do a naive random this thing, don't we still lose a bit? Like, it isn't guaranteed to be, because the SIs won't be exactly identical, right?
Exactly. Yeah, you're right. So the thing is, the algorithm is not obvious. I'm going to have to refactor the algorithm significantly. I will refactor the algorithm significantly. So towards that, let me give a different procedure. Okay? So let me sample a uniform at random tuple as before. Okay? Let me sample a uniform at random tuple as before. And now what I'm going to do is I'll run an infinite loop. So I'll just say while true. Run an infinite loop and do the following. So I'll pick a uniform at random clause, call it J. Pick a uniform at random clause, call it J. Okay. So actually, sorry, I should have. I had a step over here. I'm gonna also. I'll set a time. Let me call it L instead, because t was used for the number of trials. So I'm gonna set this thing that I call the length to 0. I'm gonna pick a uniform at random clause and call it J. I'll say if okay, so I will do L is equal to L plus 1, so I'll increment L. And then I'll say if X satisfies jth clause, just break from the loop. Otherwise, you keep going. Finally, what I'm going to set is, let me just output L divided by M. Okay, so this is, what am I doing? Sampling a uniform at random tuple as before. I'm going to set a length to be 0. You'll observe that in this, I does not appear. I don't even care for what I is. I'm just going to pick a random clause and I'm going to check, is this clause satisfied? Does X satisfy this clause? And if it does, I stop. I keep doing this. So the question is, how many trials? In this case, the trial is over here. How many experiments did I do before I succeeded? So I count the number of experiments. And once I get some number of experiments, I stop. Let's understand this random variable. Okay.
Are we also doing this t times for some t?
Yeah, we'll have, the full stitching together is going to be it's not complicated, but let's not get there yet. Let's just understand this experiment. But you're right, we are going to repeat this t times.
Okay.
But we're actually not going to repeat it t times. Well, okay, we're going to repeat it t times, but we're not going to choose t. We're not going to pre-specify t. T is going to be sort of automatically decided through this algorithm. You'll see. Okay, so what is the probability of a break at this step? So let's fix an X. What's the probability that it breaks? Any thoughts?
Would that be A over B?
No, it's not. But let's say for specific X. For a specific X. So you have some X. Now let me make, so fix an X. Fix some X. What is the probability of this condition kicking in? You picked a uniform at random clause. You're going to have to introduce some notation here.
Would it be like SI over B?
So what is SI? What is D?
Or like the cardinality of SI over B, because
I never appeared here.
That X.
So I never appeared here. This only depended on X.
Right. Oh, never mind.
So let me give you some notation here that might help. Let me say S of X is, or I'll say, I'm sorry, C of X. C of X is the number of clauses that X satisfies. Now,
Is it size of Sj over B?
it's not size of, what is D? There is no, you mean N or M?
No, we still have the same case where we see the size of some of the Okay, no.
Oh, you meant B. No, let's look at this condition. Condition. Okay, let me say. Let me do this. Let's just say conditioned on an x. So you fix some x. So let's do it step by step. Fix an x. So sorry, this was badly phrased by me. So my apologies. Probability of a break at step, this is badly phrased on my part, conditioned on x chosen in step 1. This, if you fix an x, it's exactly the number of clauses that x satisfies. Does this make sense? That is the probability of a break. Right? C of x is less than m. And in this case is actually at least 1. That's the probability of a break. This has a name. This is called a geometric random variable. So what is a geometric random variable? I'm sorry, no, this, my apologies, this is a Bernoulli. This is a Bernoulli. L is a geometric random variable, right? So this is the probability of a break. And what you do is you track how many steps it took to get to a break. So you keep flipping until you see a heads, right? And the number of flips is a geometric random variable. This is a geometric random variable. I'll get into the properties of a geometric random variable in a moment. Okay? But this is the probability that you broke at some step, that there was a break. L is the number of steps it took to break. So I will come back to the properties of a geometric random variable, but can someone hazard a guess of what is the expected value of L conditioned on X? So you have a coin. The coin has a heads probability of Cx divided by m, and you keep flipping the coin until you get a heads. How many heads do you think you need? How many flips do you think you need?
1.
It's the inverse.
It's the inverse. Right? It's the inverse of that. And so the expected value of L divided by M is the inverse of that. Okay? Now, what is the expected value of L divided by M unconditionally? It's the sum over all x in the union, right? So I look at all possible x's. I look at the probability that x is chosen times the expectation of L divided by M conditioned on x being chosen. Okay. So what do I get here? What is the probability that x is chosen?
1 over b.
1 over b? No, what is the probability that x is chosen? Not a tuple xi. What is the
right.
probability that I actually sampled x?
Yeah.
1 over a.
1 over a, no. What is the probability that I'm going to sample a tuple that contains x?
Cx over b?
Cx over b. Summation over all x in the union, Cx over b, right? Because that is, the more clauses it satisfies, the more likely it is to be chosen. Times 1 divided by Cx, and they cancel out to give you exactly a divided by b. So you're right. I mean, the expectation of this is exactly a divided by b. It's a different algorithm. Okay. I still haven't told you how this is going to lead to a more efficient algorithm. But what I have here is a geometric random variable, and the expectation of the geometric random, well, it's more like it's a geometric, every situation, every choice of x is a geometric random variable, and this is an expectation of a distribution of geometric random variables, and that actually has the right behavior. Now, the way to think about this is, if you are in this situation, the loop is going to take a long time to break. If you are in this situation, the loop is going to break much faster. So this loop is exploiting this. So what we're going to do now is we're going to globally run. So we're going to run sort of this, right? So this gives you an L. I'm going to average all the L's. I'll write this down again later over the trials. But I'm going to run this. I don't specify the number of trials. I'm going to run it until the total number of operations is O of m divided by epsilon square. It's kind of weird. Instead of specifying how many trials I have, I instead specify the total number of operations, and I'm just going to keep running this procedure, right? So this is going to sample, it's going to do a bunch of operations here, and then it's going to output something. Then I go back, I keep doing this again, I keep doing this until my total budget of runtime is exhausted, and at that point I just average all the L's that I get, and that's the algorithm. Does the algorithm make sense? The analysis is going to be non-trivial, so that's something that I will defer to the next lecture. But does the algorithm make sense?
What do you mean by a trial in this case?
So, average all the L's. So think of this as a trial. This whole process is a trial. This box. So similar to the previous procedure, right, where you had a trial that would produce some random variable whose estimate was what you wanted, whose expectation is what you wanted. Here, what you're going to do is you're not going to choose how many trials. Instead, you're actually going to budget the total runtime, the total number of operations. So what does this mean? It means that if this took longer, then you run fewer trials. And if this was fast, then you run more trials, which is exactly what you want over here. If the association check was fast, you're going to run lots of trials. If the association check was expensive, you'll run a few trials, because the association check is exactly the runtime of this process here. Right? Because we argued that the expected length, which is the runtime, is 1 divided by C of x. I'm sorry, which is no, my apology. The expected length is essentially m divided by c of x. So if c of x is small, that means you're basically in the disjoint setting. Things satisfy very few clauses. Each trial, each run of this box takes a long time, but you're going to do few of them. And in the case where c of x is large, this will terminate quickly. So you can do many more trials, which is exactly what you wanted. And therefore the product will be maintained. Does the algorithm make sense?
Yeah, now it makes sense, the last part.
To do the analysis, we are going to have to talk about geometric random variables. So once we do geometric random variables, we can come back to that. So I only have a few minutes left, but what I will do is, maybe over the next, let me start the discussion of geometric random variables. So is it clear that what's coming out of this box here is a geometric random variable? Basically, you have a coin flip, right? You have a coin flip. And you keep flipping until you get a heads. And you're looking at how long does it take to get a heads. Okay? Okay, so now this is going to sort of be a tangent. So this is how a lot of these lectures will go.
One question.
Yeah.
Yeah. Is it common to have these very, just for curiosity's sake, is it common to have these Monte Carlo-like algorithms for these problems? Because I've never seen something like this.
So is it common? You meaning are they used in practice or?
Yeah.
So
because I wouldn't think that this could have been done, but apparently it seems obvious. But
you mean, I'm sorry, so which part? This part or the previous algorithm?
Yeah, so for using these general methods to find the solutions to counting problems like this in theory.
So, yes, I mean, there are lots of... the question of, whether people use this in practice specifically for this problem, I'm not sure. But I have used methods analogous to this for like counting problems, like subgraph counting problems, where actually a lot of the algorithmics will look fairly similar to this, and using various tricks of this form, like this debiasing or this association, and then picking with that association. This is now becoming more popular, at least in the subgraph counting literature, in practice as well. In terms of whether people would use this specifically for model counting and DNF counting, I don't know. Maybe they could. I mean, this is a fairly well-behaved algorithm. But that I'm actually not sure of whether anyone has implemented this and tried this out. I should dig a little deeper into that.
Thank you.
But certainly, again, as I said, for subgraph counting, a lot of these methods work extremely well, and the algorithms have a fairly similar flavor to this. And indeed, actually, the next thing I'm going to do after I finish this algorithm is to talk about a matrix multiplication algorithm, again based on importance sampling, which is sort of eminently practical.
Just one more thing as a follow-up. So this works because it's actually easy to find the solutions to the DNF in the first place, right? Otherwise,
Exactly, for the individual clauses.
Yeah.
So yeah,
so,
but
so the problem itself has to be a well-behaved problem with.
yeah, so exactly. So in this case, what you have is, you have some kind of you're trying to count the union of you're trying to count the size of a union, and for each of the individual sets, you're able to sample within them. Right. So this is exactly the feature that you have. But this feature, it actually is shared. It appears quite commonly in many places. But you're absolutely right that you need to be able to sample from each individual set.
That makes sense. Thank you.
Yeah. So actually, I think, given that we're basically out of time, I think I'll end here. I'll take questions, and when we start the next lecture, we'll talk about geometric random variables, and then I'll give you the analysis and a better description of this sort of faster procedure.